Hello students, welcome back. Let us resume our discussion in section 3. Previously, we went through a couple of problems on absolute extrema. We have 2 more problems here, but I'm not going to go through those. Do those on your own. I'll simply show you the answer key. Plot the graph first, and then you have appropriate anticipation. Yeah, like this. And then looks like maximum 3 at 0, and then 2 pi and 4 pi and so on. And then here pi, 3 pi, and then 5 pi or negative pi and so on. Those are going to be absolute minima. And is that really the case? Well, negative infinity to positive infinity, so you don't really have to worry about the endpoints. Just take the derivative and set it equal to 0. Alright, take the derivative, set it equal to 0. By chain rule, we have this negative sign, and then just work out. Factor out, and then you're going to get sine of theta is 0, cosine of theta is negative 1. Either way, you're going to get the multiples of pi, k pi. So plug in and do your computation. Biggest is your maximum, smallest your minimum. This problem 2, I'll just show you the answer. Plot first, kind of like this, and then you can see the absolute minimum here, absolute maximum here, and the other endpoint is neither actually. So this one, plug in x equal to 0 and run your calculator. This one, plug in x equal to 2 and run your calculator. This one requires some work. Take the derivative, set it equal to 0. Let's see, how do you do that? Take the derivative and set it equal to 0, you can factor e to the x out. Exponential is never 0, so this has to be 0. And set that one equal to 0, you're going to get log of something because this is exponential equation. Yeah, that's equal to 0, and solve for exponential and then take the log. Turns out x is log of 2. So plug in x equal to log of 2 and do your computation. Turns out 1/4. That's your absolute maximum. Okay, those are absolute extrema problems, but those are little fish. Local extrema, those are far more important. Why? If you identify all local maximums, among those, the biggest is your absolute maximum. Same goes to local minima. So local maxima minima problems is far more inclusive, far more, what can I say, extensive. Yes, it's more extensive compared with absolute extrema problems. So do local extrema and then restrict yourselves to the biggest and the smallest, and that's the absolute extrema. Okay, let's go ahead. How about the first problem? Okay, alright, let's see the graph. I just plotted negative 5 to positive 5, but, well, you can adjust. If you use your handheld calculator or something, you can adjust the viewing window. I think I got a bit too big. Negative 3 to positive 3. Okay, I can see some wiggling. Negative 2 to positive 2. Okay, that's better. Negative 2 to about 1.5. Okay, I have a local maximum here, local minimum here, and that's what I'm looking for. So take the derivative, set it equal to 0, and then you can solve that. Oh, I don't have solution here. I didn't bother solving it. Okay, all right. (3x squared plus 2x minus 1 equal to 0. Take the derivative. I just took it and I set it equal to 0. What do I have here? We have a quadratic equation. 3x minus 1, x plus 1 equal to 0. Yes, positive 3, negative 2. Okay, that's right. And then what do I get? X equal to negative 1. X equals 1/3. Now, if you don't have graph, then which is local maximum, which is local minimum, or maybe neither, you have to check those. If you have graphs, then you don't have to. Well, you do have graphing calculator, and you should know how to use it. So let's go ahead. Local maximum at negative 1, x equal to negative 1. Local minimum at x equal to 1/3. Okay, how about the next problem here? Copy and paste this thing. X is going from, say, negative 5 to positive 5. Okay, I'll start somewhere, and we have something like this. Apparently, this is too big. So negative 3 to positive about 3. How about that? Not enough. Negative 2 to positive 2. Negative 1 to positive 2. Okay, I'm seeing something. Negative about 1.5 to 0.5. That's what I meant. And then this one, 1.75. Okay, in any case, I have a local minimum. And then I have an inflection point here. Neither maximum nor minimum. Does it look that way? Okay, that's an anticipation. Let's verify. Take the derivative. 12x to the third power minus 24x squared plus 12x equals to 0. Did I do this right? I can factor 12x out. And then what's left is x squared minus 2x plus 1 equals to 0. And I can factor further. 12x and then x minus 1 squared equal to 0. So x equal to 0 right here. X equals to positive 1 right here. Right here, I have local minimum. Right here, I have a critical point that is neither maximum nor minimum. And then intervals of increase and decrease. Oh, okay, all right. Well, I'll leave that to you. Decreasing, negative infinity to 0. Increasing from 0 to 1. Increasing again from 1 to infinity, like that. Details left to the students. How about some challenge problem? Something like this. Copy and paste. Less than 9, so negative 9 to positive 9. Okay, it's kind of like this. Doesn't have to go all the way to negative 9. Let's say negative about 2. Okay, like this, and then I don't see anything there. Looks like the graph is increasing up to this local maximum, and then drop down to decrease. And then what's this local maximum here? Looks like about x equals to 6, close to it. Take the derivative, set it equal to 0 to find out. But that looks a bit challenging. How to take the derivative like this? Okay, let's use the product rule. The derivative of the first function times the second function plus first function times the derivative of the second function, which is a chain rule. square root, so 1/2 negative 1/2 because subtracting 1 from the power, and then I have to multiply the derivative of the inside. Nothing changes inside, so 9 minus x, and then what's the derivative of the inside? -1. Looks like that's the derivative, and then we have to set this one equal to 0. Oh, okay, all right. So calculating the derivative is not too bad, but setting it equal to 0, and these power forms are not really good. So square root of 9 minus x, oops, plus 1/2 x, and then square root of 9 minus x in denominator. Oh, sorry about that. Okay, 9 minus x in denominator. We have negatives, so this should be negative. Okay, setting it equal to 0 was a bit challenging. How to solve this? Well, let's remove the denominator. Multiply everything by this denominator, 2 square root of 9x. If I do that, multiply by 2, no problem. Multiply by square root. That'll kill off the square root, and I'm gonna get just 2, 9 minus x, and the minus x equal to 0. What did I do? I just multiplied this 2 each term. Multiplying it here, I just lost the square root times 2, and here denominator just disappeared, and here multiplying anything by 0 will not change anything. So solving this, oh, that doesn't look too bad. 18 minus 2x minus x equal to 0. So 18 minus 3x is equal to 0. X equal to 6. And look at this. Around x equal to 6, yes. And then that's going to be the local maximum. And then increasing negative infinity to 6, decreasing from 6 to 9. I'll leave the detail to you. I just gave you a sketch. The rest is left to the students. Do I have answer key here, or I did not even bother? No, I didn't bother. I just showed you a graph. Same thing here. I'll show you the graph. So here we have this kind of graph, and apparently you're looking for this one and that one over there. And then those are local maximum, local minimum. Okay, all right. And then what's the derivative? And then set it equal to 0. I'll help you only up to derivative. Setting it equal to 0 and solving that equation is left to you. So take the derivative by product rule. 1 times 9 minus x squared, all right? First function stay the same and take the derivative. 1/2, and then subtracting 1 from the power, negative 1/2 power, and then you have to multiply the derivative of the inside. That's a chain rule, isn't it? Inside never changes, so 9 minus x squared just goes in there. And then the derivative of the inside is negative 2x, so far so good. And setting it equal to 0, you have an equation, but solving this equation looks to be a challenge. We have a square root in denominator, so killing off the denominator, and then what's left probably is going to be a quadratic equation, and that's left to the students.